Part 2. The breaking point. The closer it gets to our Sun, the more it begins to scream. Not in sound, but in light and debris. 3i. Atlas is being torn apart by the very star that made its discovery possible. As the ice of another galaxy turns to gas, we are watching a slow-motion execution of a cosmic messenger. The question is, will it survive long enough to tell us its secrets? Atlas comets, patterns, failures, and survival. Many comets are discovered under nearly identical circumstances, detected by the same survey systems as faint moving points against a static stellar background, catalogued according to standardized conventions that reduce their initial identity to coordinates and discovery dates. Yet despite this apparent uniformity at the moment of detection, their physical evolution as they approach the Sun often diverges in ways that cannot be inferred from those early parameters alone. They found by instruments optimized for coverage rather than detail, measured first through motion rather than structure, and introduced into observation at a stage when internal processes have already begun to respond to increasing solar energy, meaning that what follows is not the unveiling of an untouched object, but the continuation of a process already underway. This is the context in which the Atlas system operates, intersecting the trajectories of small bodies not at their origin or formation, but at moments when change becomes detectable, when gradual heating begins to produce visible consequences, and when the limits of structural stability start to matter. The Asteroid Terrestrial Impact Last Alert System was designed to observe large portions of the sky repeatedly, returning to the same regions night after night in order to detect motion and variation rather than to resolve fine physical detail, an approach that prioritizes temporal coverage over spatial resolution and accepts incompleteness as a trade-off for scale. By scanning wide fields instead of lingering on individual targets, Atlas records many objects briefly, capturing them during short windows when their behavior deviates enough from the background to be noticed, often at stages when they have already crossed critical thresholds of activity. This design choice shapes the entire dataset, because it means that comets detected by Atlas are frequently observed during periods of stress, rather than during long, quiet phases far from the Sun, and it is within this stressed regime that patterns of survival and failure become visible. Comets remain faint and effectively invisible while they are cold, reflecting little sunlight and exhibiting no extended structure, and it is only as solar heating initiates sublimation that gas and dust are released, forming a coma that increases brightness and allows detection by wide-field surveys. By the time this happens, however, internal temperatures have already risen, pressure gradients have begun to develop beneath the surface, and structural responses are already in motion, meaning that discovery often coincides not with the beginning of activity, but with its escalation. As a result, many comets enter the Atlas dataset already altered from their earlier state, and what is observed is not the onset of change, but its progression. As detections accumulate over time, individual comets begin to lose their isolation as singular events and instead take on meaning through comparison, where repeated observation under similar thermal conditions reveals tendencies that are not obvious in any single case but become apparent across many encounters. Some objects respond to increasing solar energy with a gradual and relatively stable rise in activity, maintaining a compact coma and coherent nucleus as material is lost steadily from a surface, while others exhibit irregular behavior marked by fluctuations in brightness, diffuse structures, and progressive loss of central condensation that suggest internal weakening rather than smooth evolution. These differences do not announce themselves clearly at first, and often emerge only after several observation cycles, as small deviations accumulate into visible divergence, hinting at underlying structural variation that cannot be measured directly but nonetheless shapes the outcome. The timing of detection plays a central role in this divergence, because comets discovered late in their approach have already absorbed substantial energy, and the processes governing their response are already in motion by the time systematic observation begins. Thermal stress does not act instantaneously, but builds as heat penetrates unevenly into porous material, expanding some regions while leaving others comparatively cold, creating internal gradients that evolve over time rather than producing immediate failure. When Atlas first records a comet, these gradients may already be well established, meaning that what appears to be sudden instability may in fact be the visible expression of a longer, unobserved progression. As this pattern repeats, it becomes increasingly clear that cometary failure is rarely the result of a single catastrophic event, but more often the culmination of multiple interacting processes that act together as heating continues, pressure accumulates, and structural cohesion is tested beyond its limits. Outgassing introduces force that is not always distributed evenly across the surface, and as jets form and intensify, they apply torque that can alter rotational state, subtly changing stress distribution and amplifying weaknesses that were previously contained. Rotation itself becomes a variable, not as an isolated parameter, but as a dynamic response to mass loss, capable of accelerating fragmentation when centrifugal forces exceed what a loosely bound structure can withstand. Within the Atlas dataset, these processes manifest as a spectrum of outcomes rather than a binary distinction between survival and destruction, with many comets exhibiting intermediate behavior that blurs the boundary between gradual decay and outright fragmentation. Some nuclei shed material progressively, producing extended dust features and diminishing brightness without ever breaking apart into discrete fragments, while others maintain apparent stability until a relatively late stage, at which point cohesion is lost and the object disperses rapidly. This variability suggests that cometary strength is not uniform, but distributed across a continuum shaped by size, composition, internal architecture, and thermal history. In late 2019, the comet designated C/2019 Y4 Atlas entered this continuum as another routine detection, initially indistinguishable from many others that had followed similar paths toward the inner solar system. Early measurements placed it on a trajectory that would bring it relatively close to the Sun, and preliminary brightness trends suggested the possibility of a prominent object, prompting increased attention as additional data were gathered and models refined. At this stage, there was little to indicate that its evolution would depart significantly from expectations, and its designation carried no implication beyond its discovery circumstances. As the comet continued inward, however, subtle deviations began to emerge that distinguished it from more stable objects, with fluctuations in brightness that did not follow a smooth trend and a coma that gradually lost definition, hinting at internal changes that were not directly observable. These signs did not point to immediate failure, but they suggested that the nucleus was responding unevenly to heating, a condition that often precedes more dramatic structural change. Only later did high-resolution observations confirm that the nucleus had fragmented into multiple components, each following a slightly different trajectory, transforming what had once been a coherent body into a dispersing system of debris. This fragmentation did not occur as a single explosive event, but as a process unfolding over time, with fragments separating gradually and activity diminishing as individual pieces became too small to sustain ongoing sublimation. The disappearance of the comet from view was therefore not abrupt, but progressive, as brightness faded and structure dissolved into the background of the sky. What remained was a well-documented sequence of change, offering insight not into an exceptional case, but into a mode of failure that appears repeatedly among comets detected under similar conditions. Cometary nuclei are particularly susceptible to such outcomes because their internal structure is defined less by mechanical strength than by the balance of weak cohesive forces that bind ice and dust together, leaving them vulnerable to disruption when that balance is disturbed. Void spaces interrupt continuity, fractures propagate stress, and the distribution of volatile materials determines where pressure builds and how it is released, creating a complex internal environment that responds to heating in ways that are difficult to predict from surface observation alone. As energy input increases, these internal characteristics become decisive, shaping whether the nucleus adapts through gradual mass loss or crosses a threshold beyond which cohesion can no longer be maintained. As these internal processes act over increasing solar distances, differences that were once marginal become amplified, and comets that initially appeared similar begin to separate into distinct evolutionary paths, not because of external intervention, but because small variations in structure and composition are exposed by sustained heating. Larger nuclei tend to respond more slowly, not because they are immune to stress, but because heat diffuses inward over longer timescales, allowing pressure to redistribute rather than concentrate rapidly, while smaller bodies with limited mass and weaker internal cohesion reach critical thresholds more quickly, often with little warning. This difference in response time alters the observable sequence of change, making some comets appear stable for extended periods before failing, while others begin to show signs of disruption almost immediately after detection. Internal architecture further modulates this response, as nuclei with more continuous material distribution can absorb deformation without concentrating stress along a single plane, whereas those with extensive voids or pre-existing fractures provide pathways along which pressure can act efficiently, accelerating the breakdown process. These characteristics are not visible directly, but their influence becomes apparent through behavior, as patterns of activity and loss reveal the hidden geometry of the nucleus over time. In this way, observation substitutes for inspection, allowing internal properties to be inferred indirectly through repeated measurement rather than direct imaging. Composition introduces another layer of complexity, because different volatile compounds respond to heating at different temperatures, and the relative abundance of these materials determines how energy is partitioned between sublimation, gas expansion, and structural stress. Comets rich in more volatile ices may experience rapid early activity that relieves pressure gradually, while those dominated by less volatile components can retain heat longer, allowing stress to build beneath the surface until release occurs in more abrupt forms. This interplay between composition and structure means that no single parameter governs outcome, and that survival or failure emerges from their combined effect rather than from any isolated property. A comet's prior history also influences its response, because objects that have approached the Sun before may already have lost their most volatile layers, leaving behind a surface that responds more predictably to subsequent heating, even as it continues to erode. Such comets are sometimes described as evolved, not because they are unchanged, but because earlier passages have already removed material that would otherwise drive rapid instability, allowing later encounters to proceed with fewer surprises. By contrast, objects making their first close approach encounter conditions that are entirely new to their structure, and their response reflects this lack of prior adaptation. Within this framework, survival is not an indication of strength in an absolute sense, but of compatibility between internal properties and external conditions, where the rate of energy input remains within the capacity of the nucleus to redistribute stress without catastrophic failure. Failure, likewise, does not imply weakness alone, but a mismatch between structure and environment, where heating proceeds faster than internal processes can accommodate. Both outcomes therefore convey information, not as judgments, but as constraints on what the object must have been like before observation began. 3I Atlas enters this landscape under circumstances that are familiar in process but distinct in origin, having been detected by the same system and observed under similar thermal conditions as many solar system comets. yet carrying material that condensed around another star and evolved under a different radiation environment. Its trajectory ensures that its encounter with the Sun is singular rather than repetitive, removing the moderating influence of prior passages and placing its current behavior in a context where initial conditions matter more strongly. The activity observed so far remains moderate, and the nucleus appears intact, but these observations are bounded by distance, brightness, and the finite duration of favorable viewing geometry. Comparisons between 3I Atlas and solar system comets must therefore proceed cautiously, not because the processes involved are unfamiliar, but because the assumptions underlying those processes differ, and patterns derived from one population may not translate directly to another. What can be compared are responses to heating and stress, rather than long-term evolution, allowing shared physical mechanisms to be examined even when formation histories diverge. In this sense, 3I Atlas extends the Atlas dataset outward, linking local observations to material formed in another stellar environment. At the same time, the limitations of the Atlas system shape what can be known, because its observational strategy favors detection and tracking over prolonged, detailed study, often recording objects only during brief intervals when their behavior becomes conspicuous. Many comets appear in the data already altered, their earlier states unobserved, creating gaps that cannot be filled and requiring interpretation to remain provisional rather than definitive. What appears sudden may be the visible endpoint of a longer process, and what appears stable may simply not yet have reached a critical threshold. Despite these constraints, the value of Atlas lies in accumulation rather than completeness, as repeated observation under comparable conditions allows relative frequency to replace anecdote, and pattern to emerge where isolated cases offer little guidance. Fragmentation events, gradual decay, and sustained activity each occur often enough to be recognized as characteristic responses, shaping expectations for future detections without eliminating uncertainty. This context does not predict individual outcomes, but it narrows the range of plausible behaviors that new objects may exhibit. With this framework in place, 3I Atlas can be understood not as an isolated curiosity, but as part of a continuum of small bodies responding to energy input and structural limits, even as its interstellar origin expands the scope of interpretation beyond the solar system. Its significance lies not only in what it does, but in where it fits, connecting familiar physical processes to material formed elsewhere and extending local observation into a broader astrophysical context. Seen across the full Atlas dataset, what emerges is not a narrative of isolated successes or failures, but a landscape of responses shaped by exposure to energy, where each comet traces a path determined by how quickly it absorbs heat, how efficiently it releases pressure, and how evenly stress is distributed through its interior. This landscape is not static, because the conditions under which comets are detected vary with geometry, distance, and timing, and the same physical object might appear stable under one set of circumstances and unstable under another, depending on when and how it is observed. Atlas does not capture these objects continuously, but it intersects their evolution at moments when change becomes visible, offering snapshots that, when assembled, reveal a broader pattern of behavior. Failure, when it occurs, is therefore not an anomaly to be explained away, but an outcome that must be accounted for, because it constrains the range of internal structures that cometary nuclei can possess while still remaining intact under similar conditions. Each fragmentation event reduces uncertainty by eliminating configurations that would have survived the same thermal environment, even if the exact pathway to failure cannot be reconstructed in detail. In this sense, destruction functions as a filter, narrowing the space of possibilities and shaping scientific understanding through absence as much as through presence. Survival plays an equally important role, because comets that endure sustained heating without catastrophic breakup demonstrate that fragile does not mean transient, and that certain combinations of size, structure, and composition allow gradual erosion without loss of coherence. These objects persist long enough to be observed repeatedly, providing continuity across multiple observation cycles and allowing changes to be tracked over time rather than inferred from isolated measurements. Their behavior anchors the dataset, offering reference points against which more unstable cases can be compared. Together, survival and failure define the boundaries within which cometary evolution unfolds, outlining a regime governed not by single parameters but by the interaction of many variables acting over time. ATLAS, by observing a large number of objects within this regime, transforms individual outcomes into a comparative framework, where frequency replaces exception and pattern replaces anecdote. It does not eliminate uncertainty, but it structures it. Within this structured uncertainty, 3i ATLAS acquires meaning that extends beyond its immediate behavior, because it can be placed alongside a population of objects whose responses to heating and stress have already been observed, even if their origins differ. Its interstellar provenance introduces new variables, but the physical processes it experiences are familiar, allowing insights gained from solar system comets to inform interpretation without dictating it. In this way, 3i ATLAS acts as a bridge, connecting local observational knowledge to material formed under different stellar conditions. The limitations of this comparison remain significant, because interstellar objects are rare and the sample size is small, preventing definitive conclusions about how representative any single case might be. Yet rarity does not negate relevance, because even a small number of observations can constrain models of planetary system formation and evolution when those observations involve material that cannot be accessed in any other way. Each interstellar visitor adds a point of contact between theory and observation, expanding the empirical foundation upon which broader inferences can be built. As survey capabilities improve and detection rates increase, the context provided by systems like ATLAS becomes increasingly valuable, because it establishes a baseline against which new discoveries can be interpreted, allowing unfamiliar objects to be placed within an existing framework of physical response. This framework does not prescribe outcomes, but it guides attention, indicating which behaviors are common, which are rare, and which may signal underlying differences in structure or origin. With this perspective in place, attention can now shift beyond detection and behavior toward origin, as interstellar objects are considered not only as transient visitors, but as fragments of planetary systems formed around other stars, carrying information about processes that shape worlds across the galaxy. The next part moves outward in scale, from individual comets and survey systems to the environments that produce and eject such objects, asking what their presence reveals about how planetary systems form, evolve, and interact with their surroundings.